Hello everyone, welcome to the third topic in the Physics SS3 first term curriculum. Now the topic for the third topic we are looking at here in the curriculum is electric field. Now if you've been following our videos so far, please we'd like you to drop a comment. If there's any particular question you have in mind concerning what we have done so far, please drop them in the comment section. And if you are seeing this video for the very first time, this is our channel Oya Learn, where we continually give you helpful academic videos like this, where we explain concepts that are to be taught in class in a way that is easily understood. Trust me, if you follow our videos, you are on your way to acing physics and any other subject that you pick that we find right here on our channel. We have multiple videos cutting across different classes, so please pick out the video that is in the playlist for your own class grade, and always drop a comment as to if there's anything you'd like us to discuss, if there's anything you'd like us to explain, and we'll definitely attend to all of your questions. And don't forget to subscribe to the channel and also like the videos, and help others to also improve in their academics by sharing the videos so that they too can have access to this beautiful work that we are doing right here on Oya Learn, your flawless school too. Now, to what we have for this topic, under electric field, I will be considering first the concept of electric field, where we'll define what electric field is, and then we'll look at what force between point charges are. At that point, we'll be looking at what is known as the Coulomb's law. Now, the Coulomb's law is a very interesting law. We'll state the law and we'll look at the mathematical formula that you can get from the Coulomb's law. After that, we then define what is known as the electric line of force. That is when you have 2-point charges, what kind of field do you have there, and what is the line of force between the 2-point charges. After which we'll then look at electric field intensity, we'll define it, we'll state the equation and apply it to solve some problems. And the same thing with electric potential and potential difference. Now, when we are done with that, we'll now go into capacitors and capacitance. Starting with what a capacitor is, we'll look at the components that make up a capacitor and then the function of a capacitor. Then we learn how to calculate the capacitance of a capacitor. After we've done that, we'll then look at arrangement of capacitors, because you can arrange capacitors in two ways, whether it's in series or in parallel. So we'll be learning how to find the resultant capacitance of capacitors that are connected in series and parallel. Mind you, in some cases you'll find both series and parallel connection in one circuit. So we'll be showing you how to solve problems like that as well. After that, we then look at the energy stored in a capacitor, and then we wrap up the entire class by solving multiple problems on the topic electric field. At this point, we'll be picking questions from JAMB exams, from WAEC exams, and other types of exams. Questions that borders on electric field, capacitors, and capacitance. So trust me, you don't want to miss any part of this class. Ensure that you have your writing materials close by, because we'll be giving you tips as we go along, especially when we begin to solve problems. You'll be getting some tips on things that you need to know that help you solve questions more accurately, and some facts that are not always stressed when you are talking about electric field. So take note of those things, and if you should have any question on any of the parts of this topic, please ensure that you drop it in the comment section and we'll attend to all of your comments. Thank you so much. Now let's dive into electric field. In our last lesson, when we talked about the gravitational field, we established that there is a force of attraction between two objects of known mass. And just like there is a force of attraction between those such objects, there also exists a force of either attraction or repulsion between 2-point charges. Now, this force is something, the magnitude and the nature of the force is what French physicist Charles Coulomb set out to investigate. And he discovered that when you have 2-point charges such that they are small when you compare it with the distance between them, he found that the force that exists between these 2-point charges can be given by the equation F, which is inversely proportional to the square of their distance. So from his investigation, he developed this. This is what we know as the inverse square law. The inverse square law. So let's call this statement 1. Now, upon further investigation on the nature and magnitude of the force between point charges, he also saw that the force between the point charges is directly proportional to the product of the charges. So that is, we have charge Q1 and charge Q2. The force between them is proportional to the product. So Q1, Q2. So let's call this statement 2, while this is statement 1. Now, the combination of these two statements leads to what we know as Coulomb's laws, which state as follows. So we say Coulomb's law states that the force between 2-point charges Q1 and Q2 separated by distance R is directly proportional to the product of the charges, and inversely proportional to the square of the distance between them. So what this says is, let's just restate it for clarity. Coulomb's law states that the force between 2-point charges Q1 and Q2 separated by distance R is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Hence, we can then say F is proportional to Q1, Q2, all divided by R squared. And don't forget that when you are dealing with statements from laws like this, you have to develop an equation. So let's go on now to develop an equation for this and get the constant of proportionality, including the value of that constant. So from the Coulomb's law, we already have this. F proportional to Q1, Q2 divided by R squared, right? Now, when you take away this proportionality symbol and bring in the equality sign, you have to introduce a constant. So F therefore equals K, Q1, Q2, this should be Q2, now divided by R squared. Now you see, the constant of proportionality according to Coulomb's law equals 1 over 4 pi epsilon naught, where epsilon naught is known as permittivity of free space. Permittivity of free space. Okay? And the value of this 1 over 4 pi epsilon naught would give you 9.0 times 10 to the power of 9. And it is in newtons meter squared per coulomb squared. Okay? But when we put all of it together, we can then say F equals 1 over 4 pi epsilon naught Q1 Q2 divided by R squared. Okay? Or you just say it is 9.0 times 10 to the power of 9 multiplied by Q1 Q2 over R squared. And all of this will be measured in newtons in the end. So this is the equation for Coulomb's law. Let's solve a few questions using this equation now. In this question, we are to find the force of repulsion between two protons of the charge is 1.6 times 10 to the power of negative 19 coulombs. Now, if the distance between them is 5.3 times 10 to the power of negative 11 in meters, and taking the constant of proportionality, which is 1 over 4 pi epsilon naught, as 9.0 times 10 to the power of 9 Newton meter square per coulomb square. So let's apply Coulomb's law to solve this problem. And here's the solution. We have that the force, remember, it's force of repulsion because we have two protons, and protons are positively charged, and two like charges will repel each other. So that is why it's force of repulsion. Now this equals 1 over 4 pi epsilon naught Q1 Q2 divided by R squared. So from here we have F equals, now all of these has been summarized as 9.0 times 10 to the power of 9. So we multiply that by Q1, which is 1.6 times 10 to the power of negative 19. And then by Q2, which is also the same charge. They have the same charge. So that will be 1.6 also times 10 to the power of negative 19. And all of this would be divided by R squared. So R is given here as 5.3 times 10 to the power of negative 11. So we'll put this in brackets and then we'll square. Now, all you need to do is apply your calculator. You can work with the numerator first, then the denominator, and then whatever you get, you divide them by each other, and that gives you the force to be 8.2 times 10 to the power of negative 8. And don't forget that force is measured in newtons. And this is the solution to this problem. Here's another question where we have to calculate the force between two charges. But this time we have a positive charge and a negative charge. The positive charge is 10 coulombs and the negative charge is negative 20 coulombs. So as you guessed right, the kind of force that will be here is the force of attraction. And we are told that the charges are 3 meters apart. And we are to take 1 over 4 pi epsilon naught as 9.0 times 10 to the power of 9 newtons meter square per coulombs squared. So you can pause the video, try to solve this question yourself, and then compare your answer with what is gotten at the end of this video. And don't forget to leave us a comment if you got the answer correctly. Now, here's what I expect that you should have done. Solution. Now, the force of attraction equals 1 over 4 pi epsilon naught Q1 Q2 all divided by R squared. Now, the fact that this is a negative charge does not mean that you are impute negative 20 in your formula here. You just say F equals, now this gives you the value of 9.0 times 10 to the power of 9 newtons meter square per coulomb square multiplied by Q1, which is 10 coulombs, multiplied by then 20 coulombs. Okay? Now, all of this will be divided by R squared, so we have 3 meters in bracket squared. So what does this give us? Now, we're going to be having 9.0, of course, times, now this will give us 10 times 20, and that is 200. Okay? All of these times 10 to the power of 9. This is Newton meter square per coulomb square, and then we have coulomb square here. So coulomb square cancel per coulomb square, of course. So all of this divided by 9 meter squared. So meter square cancel meter square. 9 here 1, 9 here 1. So our final answer here, we have 200 times 10 to the power of 9, and this is in Newton, which can then be written as 2.0 times 10. So we're going to add 2 to this, and that will give us 11 Newton. And this is the solution to the question. I hope you got the same thing, and don't forget to leave us a comment if your answer is correct. We have seen from Charles Coulomb's work how that 2-point charges exert a force on each other, and we've been able to calculate the force of attraction, force of repulsion between 2-point charges using some examples. But here it begs the question, how can a charge exert a force on another charge even though they are not in contact? And the answer to that question is revealed in the concept of electric field. According to Michael Faraday, a charge has a force that extends from the center of that charge to every other point on the universe. That is, when you have a point charge like this, it spreads out its force or its influence, electric force of influence, all around it. So that is, whenever you place any other charge within the space that this particular charge is, they come under the influence of this charge. It's just kind of like when we were discussing about gravitational field earlier, that you have a massive object, and then we said around that massive object there exists a force field, right, that pulls other objects towards the center of that massive object. The same thing exists for point charges. So that is, when you have a charge like this, around this charge there is an electric force field that spreads out from the center of this singular charge. So anytime another charge comes close to this charge, it falls under the influence of this electric field, and that influence creates what we now know as force field. Hence, electric force field. Okay? And to define this, Michael Faraday proposed that an electric field can be defined as a region or a space where electric force is experienced by a charged body. So let's put that down. An electric field is a region or space where electric force is experienced by a charged body. So only charged body interact with another charged body when they come within its electric field. When you have a positive charge and you bring another positive charge within that field, it experiences a force of repulsion. By the time you bring a negative charge, it will experience a force of attraction. But when you bring a neutral charge, because it is not a charged body, it does not experience the electric force field. Okay, this leads to what we know as the fundamental law of charges, where we say like charges repel each other, while unlike charges attract each other. So to summarize what Michael Faraday proposes here is that just like in the case of gravitational field where large bodies pull others to themselves, in the case of electric field also, every charged particle has a force field around them to which they either attract or repel other charged body when they come within that region or space known as that particular charged body's electric field. We can test an electric field by placing a small positive charge within the field. Now you have to make sure that the test charge is significantly small such that the force it exerts on the field does not alter the effects of the electric field you are testing. Okay, now when you do that, you can then easily map out the electric field by drawing lines. Now, these lines drawn here that map the electric field is what is known as the electric line of force. Now, how do we define what is known as electric line of force? Electric line of force is an imaginary line whose direction at any point represents the direction of the field, the electric field, at that point. Another way to define it is to say that electric line of force is the path that an isolated positive charge will follow in an electric field. So basically, when you put a unit positive charge in an electric field, the path it follows draws out or maps out what we know as the electric line of force. Now let us define the strength of an electric field, or what is known as electric field intensity. Okay, the strength of an electric field, the strength of an electric field or electric field intensity E at any point is the force per unit charge Q at that point. Now, this is the simple definition for what is known as the electric field intensity. Mind you, it's either you call it electric field intensity or you say the strength of an electric field. So it is the force per unit charge Q at that point. Now, to write this in equation form, we'll say electric field intensity E equals force per unit charge Q. And it is measured in Newton per coulombs. Now, here's one thing you need to bear in mind. There are different ways you could be asked to find the electric field intensity at any point in an electric field. Now, this is one of the equations that works, but don't forget we have already derived an equation for the force between 2-point charges. And in that case, we said F. Okay, so we can say but F itself is what? 1 over 4 pi epsilon naught. So two charges now, let's call the first one Q and then the second one charge Q divided by R squared. So if this is the case, and then we can find another equation for E by saying E equals this force now, which is 1 over 4 pi epsilon naught Q over R squared divided by Q. Okay, what this implies is that you now have Q divided by 4 pi epsilon naught R squared, all of these times 1 over Q. When you change this to multiplication sign, of course you have to write this as the reciprocal of what it is now. So that's why we have 1 over Q here. And easily you see Q cancel Q. So electric field intensity E can then be written as the charge divided by 4 pi epsilon naught R squared. So it's either you use this equation or you use this equation. Both of them work for finding the electric field intensity at any point in an electric field. Now let's solve two questions, one for each of these equations, so that you see how it is applied when solving questions. Calculate the electric field intensity in a vacuum at a distance of 10 centimeters from a charge of 5 times 10 to the power of negative 4 coulombs, taking 1 over 4 pi epsilon naught as 9 times 10 to the power of 9 newtons meter squared per coulomb squared. Now here's the solution. You see that in this question we have that we are to find electric field intensity E when we are given Q equals 5 times 10 to the power of negative 4 coulombs. We are also given R to be 10 centimeters, which is 0.1 meter, and then we are given 1 over 4 pi epsilon naught as 9 times 10 to the power of 9 newtons meter squared per coulomb squared. Okay, so the equation that works in this case is E equals Q over 4 pi epsilon naught R squared. Now when we apply this, what you have here is 1 over 4 pi epsilon naught already, which you can get as 9 times 10 to the power of 9 multiplied by Q. Now Q itself is 5 times 10 power of negative 4, all divided by R squared now, which is 0.1 squared. So what we have here is 9 times 5, that is 45, times 10. 9 minus 4, that will give us 5. All divided by 0.1 squared, that is 1 times 10 to the power of negative 2. Okay, so from here we can now see that E equals, now this, when you compute all of this, you get 4.5 times 10 to the power of 8. And don't forget, it is measured in newtons per coulombs. And that's the solution to this question. In this question, we are to calculate the force acting on a charge 1.6 times 10 to the power of negative 19 coulombs in an electric field of electric field intensity 5.0 times 10 to the power of 5 newton per coulomb. So here we have the electric field intensity and we have the charge, and we have to find the force. So to solve a question like this, here's what you do. The relationship between force, electric field intensity, and charge is given by E equals F over Q. And since we are to find the force, it implies that the force on the charge is therefore the product of electric field intensity and the value of the charge. So now we can solve for the force by having electric field intensity 5.0 times 10 to the power of 5 newton per coulombs multiplied by the value of the charge, which is 1.6 times 10 to the power of negative 19 coulombs. So per coulombs, that cancels out. So what we have here is in newtons. So F equals 5.0 times 1.6, that will give us 8.0 multiplied by 10. Now we have, if you're applying the law of indices here, we'll have 5 minus 19, and this is in newton. So we have 8.0 times 10. Now 5 minus 19 will give us minus 14, and it is in newtons. And that's the solution to this question. Let us consider a particular electric field with this line of force like so. And then you have another positive charge at point A like this. And then you are tasked with bringing this positive charge from this point to this point here. Now, and this is work that will have to be done against the electric field from this charge. The work done to move this charge to this point is what is known as electric potential. It is defined as the work done in moving a positive charge from infinity to a point in an against electric field. So let's put that down. Electric potential is defined as the work done in bringing a unit positive charge from infinity to a point in an electric field against the effect of the electric field. So there is going to be some resistance from the electric field. So the work done to bring that unit positive charge from infinity to a point within the electric field is what is known as electric potential. Now, let's assume we then have another charge at this point B. We presume that you are required to apply more force to bring A to a new point than that of B. So this gives rise to what we know as potential difference, because A has more electric potential than B. Okay, so since the electric potential at A is more than the electric potential at B, we have what is called potential difference there. So we can now say potential difference let's denote this VAB, is the work done to bring a charge from a point A to another point B against an electric field. So basically, since you need more work to bring A to a new point B, that gives rise to the potential difference. So that extra work that is done is what we actually know as the potential difference. So when it comes to calculating for the potential difference here, we say V equals the work done over the charge. And this same equation can be written as, V equals E, which is electric potential, times the distance. Now, we can work out another equation for V, since we know that E itself is what? Q over 4 pi epsilon naught R. Now, instead of R, now we put D there, okay? Squared. So if this is the case, what this implies now is that V therefore becomes, now we're going to multiply this by D. So we are having Q over 4 pi epsilon naught D squared multiplied by D to give us Q over 4 pi epsilon naught D. Now this is another equation for electric potential. So if you are not using this one, then you are using this equation. Let's solve some examples of such questions so that you see how you apply either of this equation. This question says, calculate the potential at a point 50 centimeters from a charge 2.5 times 10 to the power of negative 6 coulombs, taking 1 over 4 pi epsilon naught as 9 times 10 to the power of 9 Newton meter square per coulomb square. Now, when you have a question like this, here's what you do. Don't forget that since this is in centimeter, you have to bring it to meter. So the distance D here which is 50 centimeters, becomes 0.5 meters. Okay, we have the charge itself, Q, as 2.5 times 10 to the power of negative 6 coulombs, and then we are given 1 over 4 pi epsilon naught as 9 times 10 to the power of 9 newtons meter square per coulomb squared. Okay, so in order to solve for the potential here, V equals Q divided by 4 pi epsilon naught D. Now, what does this mean? It means we have 1 over 4 pi epsilon naught multiplied by Q, all divided by D. So let's see what this would give us. Now we have V equals, this part gives us 9 times 10 to the power of 9. Now, all of this multiplied by Q. Q itself is 2.5 times 10 to the power of negative 6. Okay? Now we say all divided by D. D itself is 0.5 meters. Okay? So to work with this, what do? We can rewrite this and say 9 times 10 to the power of 9 times, this can now be written as, okay, we have this as 2.5 already, times 10 to the power of minus 6. Now we can write this and say 5 times 10 to the power of negative 1. So that we can easily break this down and say this here goes once, here we have 2. Okay? Now what we have here is 9 divided by 2, so V becomes 9 divided by 2 will give us 4.5. Okay? So times 10. Now what we have to do is 9 minus 6. And then when this comes out, it becomes plus 1. Okay, so this is 10. 10 minus 6 will give us 4. So what we have is 4.5 times 10 to the power of 4. And don't forget that it is measured in, now remember that this is electric potential. And what we have learned so far, now what is the unit that we have here? This is coulombs. Let's bring out all the units from what we have here. Okay, this is Newton meter square per coulomb squared. We multiply that by what we have here, which was in coulombs, and then we have here in meter square. So meter square cancelled meter square. Coulombs take one of these. So what we have is in Newton per coulomb. And that's the solution to this problem. In this question, we are to calculate the potential difference at a point 50 centimeters from a charge 2.5 times 10 to the power of negative 6 coulombs, taking 1 over 4 pi epsilon naught as 9 times 10 to the power of 9 Newton meter square per coulombs squared. Now, when you have a question like this, here is how you solve it. In this case, potential difference V will be given as Q over 4 pi epsilon naught D. Okay? And what this basically means is we have 1 over 4 pi epsilon naught multiplied by Q divided by D. So all we have to do is apply this, and then we'll find our answer. So V equals, now this part already is given here as 9 times 10 to the power of 9. Okay? And this is in Newton meter square per coulomb squared, multiplied now by Q. Q is given as 2.5 times 10 to the power of negative 6, and this is in coulombs, all divided by the distance, which is 50 centimeters, converted to meter will be 0.5 meter. So from here we can see meter takes out one of these, coulomb takes out one of the per coulombs, and then we can solve what we have left. Now, in order to tidy this up, I'm going to write this part in standard form, so that we have 9 times 10 to the power of 9 multiplied by 2.5 times 10 to the power of negative 6, all divided by 5 times 10 to the power of negative 1. And this is, what we have here is Newton meter per coulomb. Okay? In other words, this can be written as volts. Okay, so it's either Newton meter per coulomb or volts. So from here, we can easily see that 5 goes here once, 5 goes here, 2.5 goes here once, 2.5 here twice, I mean. So now we have 9 divided by 2. So V therefore becomes 9 divided by 2. That gives us 4.5. Okay, and then we'll be having times 10. Now applying laws of indices, that will give us 9 minus 6. And when this goes up, it becomes plus 1. And Newton meter per coulomb can be written as volts. Now this would give us 4.5 times 10. Now 9 plus 1 is 10. 10 minus 6 and we have 4. And it's in volts. And this is the solution to the problem. Here is another question that says, two parallel plates are charged to a voltage of 40 volts. Now, if the plates are separated by a distance of 10 centimeters, calculate the electric intensity between them. And before I go on to show you how to solve this question, if you are still not subscribed to the channel, kindly take a moment of your time to click the subscribe button. Alright, and you can also ensure that many of your friends who need the kind of content that we create right here on Oya Learn get access to them by sharing the video. They are just a share away from getting access to what we do right here on our channel. So please ensure that you share the video and encourage them also to engage with the video by liking and also dropping a comment. And don't forget that if you have any question at all on any of the work that we are doing, or perhaps during your own study time, you came across a particular aspect that you require some help with, kindly drop them in the comment section and we promise to attend to all of your comments. Thank you. Now, down to this question. To solve it, what we do is very simple. We already know that the relationship between the electric potential, the electric intensity, and the distance is given by the equation V equals ED. Okay, where V is the potential, electric potential, E is electric intensity, D is the distance between them. So since the question asks that we find the electric intensity, it implies that electric intensity equals V over D. Okay, don't forget that the distance has to be in meter. This is already given in centimeter, so we have to convert that to meter. So electric intensity here becomes V, which is 40 volts, divided by D. 10 centimeter converted to meter will give you 0.1 meter. Okay, now this when calculated will give you 400 volts per meter, or we just say 400 Newton per coulomb. And that's the solution to this question. Now let us go to the second part of our study of electric field, and this part deals with capacitors and capacitance. Okay, now the first thing we want to do here is to know what a capacitor is. So when you're asked to define or describe a capacitor, you should know that a capacitor is an electronic device that is used to store electric charges. Okay, let's put that down. A capacitor is an electronic device used to store electric charges. So when you have a capacitor in a device, it does the function of storing electricity, right? It's more like a bank where you save electric charges. Now, what a capacitor is made of is mainly two metallic plates. So we have, in a capacitor, we have two metallic plates like this. So let's assume this is a capacitor connected to an electric cell. This would be our electrolytic cell here. Okay, so we have an electric cell here. This are the plates of the capacitor. Now here's the thing, the plates carry different charges. So when this plate that is connected to the positive terminal of your cell will be carrying the positive charges, okay, don't forget, this plate is connected to the positive terminal of your cell, hence it carries the positive charges, while this one connected to the negative terminal of the cell will carry negative charges. Okay, so let me just add more charges here so that it balances out. Okay, so now here we go. We have two plates, parallel plates in the capacitor. Now these plates are separated by distance d, a very small distance. It's a very small distance, so it's important that I stress that fact. Okay, now we have two plates separated by a small distance. Now within this space here, what we have is, it's not empty. Okay, it's not always like that. What we have here is what we call a dielectric. Okay, a dielectric. So what we have here, let's label that as a dielectric. It's a special type of insulator. Okay, so it's called a dielectric. Now what we have here, this and this are the plates of the capacitor. So this is what a capacitor is made up of. So let's recap. A capacitor is an electronic device used to store electric charges. Okay, now if you are to describe it, you now say it consists mainly of two parallel plates carrying opposite charges. Separated by a small distance d, containing a special insulator called a dielectric. So this is how you define a capacitor, while this is how we describe a capacitor. Now before we go on to look at how we find the capacitance of a capacitor, or to define what we call the capacitance of a capacitor, it is important to know that while working in electronics, or even in the field of physics, electricity, electric field and the likes, whenever we are talking of a capacitor, you are not always going to see this diagram. Okay, so we use something called electronic symbol to represent capacitors. And the electronic symbol for a capacitor looks like this. You have a line like this, and then you have two parallel lines of the same height. Please do not confuse this with a cell. You see, in the case of a cell, one of the parallel lines here is shorter compared to the other, so that you can identify the positive and negative terminal of a cell. Now in a capacitor like this, what you have is this. Okay, and because there are different type of capacitors, some of them do have the positive and negative symbol indicated there. Okay, like when you're talking of electrolytic capacitors, most times there is a different kind of symbol for electrolytic capacitor. You may see something like this as a symbol for a capacitor. Okay, this is what we call electrolytic capacitor. Okay, and depending on other types, so when we talk about types of capacitor, I'll be showing you some of them and their symbols, okay, where necessary. It's not in all of them that we are supposed to look at this point in time. Okay, because what we are looking at here is to be able to define what a capacitor is, describe what it looks like, and also calculate the capacitance of a capacitor. But you know how we do right here on OYLN, we ensure that we give you all necessary details so that you have a well-rounded knowledge on the topic, okay? But just in case you're asked, don't forget that if you're asked to define a capacitor, you say it's an electronic device used to store electric charges. And if you're asked to describe a capacitor, you have to mention that it consists mainly of two parallel plates carrying opposite charges separated by a small distance d, which contains a special insulator known as a dielectric. And that's how we define and describe a capacitor. Before we go into the different types of capacitors, it's important that we understand the concept of capacitance of a capacitor. Now that we know what a capacitor is, that is the electronic device used to store electric charges. Now, the amount of charges they store varies from one capacitor to the other, and this is dependent on what we know as the capacitance of a capacitor. So to define the capacitance of a capacitor, I will say it is the ratio of the charges on either plate of the capacitor to the potential difference between them. Let's put that down. The capacitance of a capacitor is defined as the ratio of the charges on either plates of the capacitor to the potential difference between them. Okay, so that is when you're asked to find the capacitance of a capacitor, it can be given by the equation C equals Q over V, where C is capacitance, then Q is charge, and then V is potential difference. Okay, now going by this, we can then say that capacitance is measured in, because since C equals Q over V, which is, this is measured in coulombs, this is measured in volts, so that is capacitance is measured in coulombs per volt. Okay, however, you see what we know as coulombs per volt is denoted farads, okay, or F. So that is capacitance of capacitors is measured in farads. Okay, now because most of the capacitors that we use, especially when you talk about any kind of machine or device or appliance around the house that involves the use of a motor, talking about things like the fan, the pumping machine and the likes, they contain, even your blender, they contain capacitors. Now those capacitors are very small, so the capacitance are measured in what we know as microfarads. So you can have them in multipliers. You can have millifarads, you can have microfarads, you can have nanofarads, you can have picofarads. I hope you haven't forgotten what the sub-multiples are. When we say milli, milli is times 10 to the power of negative 3. Micro is times 10 to the power of negative 6. When we say nano, that is times 10 to the power of negative 9. And then pico is times 10 to the power of negative 12. So these are what we call sub-multiples. So because the kind of capacitors we use in those kind of devices store very small charges. Okay, so they are measured in sub-multiples of farads. You can find some in microfarads, you can find some in nanofarads, some in picofarads, some in millifarads, depending on the amount of charge that they store. Now, at this point, I would mention that when it comes to calculations involving the capacitance of a capacitor, it is not limited to this equation alone. Okay, because you see the capacitance of a capacitor depends on two things. Okay, the capacitance itself is directly proportional to the area of the individual plates of the capacitor. Okay, so that is depending on how large the plate is. When the plates are large, it stores more charges. When the plates are very small, it stores less amount of charge. And the same capacitance, C, is inversely proportional to the distance separating the plates of the capacitor. Now, when you combine these two, we now say capacitance is proportional to the area divided by the distance separating the plates. Now, working with this, by the time you remove the proportionality symbol and bring the equality sign, you have to bring in a constant known as permittivity. So, this over D. Now, note, this is known as permittivity. Permittivity. Okay? And it depends on the dielectric between the plates of the capacitor. Okay, so when we have a vacuum, when there is a vacuum between the plates, this then becomes permittivity of free space. Okay, and this is approximately 8.9 times 10 to the power of negative 12 farads per meter, thereabout. Okay, but when you have other types of dielectric materials, permittivity therefore becomes the multiple of permittivity of free space and relative permittivity. So note, this is known as relative permittivity. Okay, so depending on the manner the question is being set, when you're asked to find the capacitance of a capacitor in a place where you have the charge on either plate and the potential difference between the plates, then you can easily use this equation to find the capacitance. But in a situation where you are asked to find the capacitance of a capacitor and the information that you have is around either the distance between the plates and then the area between the plates. See, sometimes you may not even be given the area between the plates and be given perhaps the length of the plate or the thickness of the plate, and using that you can also find the area of the plate based on your knowledge of geometry. Okay, but most times you will be given the area of the plate. So when you have the area of the plate and you have the distance between them, you will also be given this constant. See, it is not a particular figure. Okay, it is approximate. Okay, so you'll be given a figure that is close to this as well to apply when you have permittivity of free space. That is when the plate is separated by a vacuum. But when it is not separated by a vacuum, you may be given the value of the permittivity itself, or be given the value of permittivity of free space and relative permittivity, which you will then multiply together and then apply it in the equation C equals epsilon naught epsilon R A over D. Then when you apply this, you can also get the capacitance of that capacitor. So these are all the equations that help you to solve questions on capacitance of a capacitor. So we'll solve some of them. We'll give quite a number of examples that involve using these equations, and then you see how you apply them in real time. But before then, let us look at types of capacitors. There are three main types of capacitors. Two of them are ones that we are very much familiar with. The third one is a special type of capacitor. So we just named those ones special capacitors. But let's start with the most common capacitors that we have. The first category of capacitors we have is known as fixed capacitors. Now, you see, these particular capacitors have a fixed capacitance. That is, any capacitor at all that has a fixed capacitance is called a fixed capacitor. Let's put that down. These have a fixed capacitance. So that is when you have a capacitor that only offers, say, 10 microfarad of capacitance, that particular capacitor is a fixed capacitor. You could also find some in thousands of microfarads, some in even picofarads, in nanofarads, and the likes. Now, under this group of capacitors, we have different examples from the electrolytics examples. Electrolytic capacitor, electrolytic capacitor. This is a fixed capacitor. We also have the mica capacitor, and so on. All of these are fixed capacitor, and their symbol are, so it's either you have this or these are symbols for fixed capacitor. So whenever you are dealing with any question in physics that involve capacitors and capacitance of capacitors, you may see this symbol or this symbol. Now when you see something like this, it means that the capacitor involved there is a fixed capacitor. From the non-electrolytic to the electrolytic capacitors that we have under this group known as fixed capacitors. Now, don't forget, the main thing here is that these particular capacitors have a fixed capacitance. That is, they have the capacitance that they offer. They do not give more or less than that amount of capacitance. Now, to the second group, we have what is known as variable capacitors. Now, these capacitors have a range of capacitance, and it can be altered in a circuit. Okay, so when you have a particular capacitor that has a switch to it or a knob to it, to which you can either increase its capacitance or reduce the capacitance, those type of capacitors are what we call the variable capacitors. Okay, and they have the symbol. The symbol for variable capacitors look like this. You see something like this with an arrow across it. Okay, this tells you that it's a capacitor that has a range of capacitance that can be altered within the circuit. You can either increase it or reduce it depending on how you want the circuit to function. And then, of course, the final type are called the special capacitors. These ones have very high capacitance. Okay, they are only produced to perform special functions, and they also have different types at this level, from the glass capacitors to the super capacitors and the likes like that. So don't forget, these ones serve a special purpose. So whenever you are dealing with a special kind of electric circuit that requires the storage of high amounts of charges, you will most likely be using a special capacitor in that scenario. But when you are dealing with simple circuits that require a fixed amount of capacitance, in that case, you'll be using the fixed capacitor, whether it's electrolytic or non-electrolytic. Okay, and then when you are dealing with a circuit that requires you to always change your capacitance depending on the kind of output you want, then in those cases you would be needing a variable capacitor, which gives us the three main types of capacitors that we have, from fixed capacitors that have fixed capacitance, to variable capacitors that have a range of capacitance, and then to special capacitors that store very high charges because they have high capacitance. And that's all the types of capacitors we have. This question says, a capacitor has a charge of 2 times 10 to the power of negative 4 coulombs and is connected to a 100-volt source. Now, what is the capacitance of the capacitor. Now remember that when we talked about capacitance of capacitor, we did mention that the capacitance is the ratio of the charge to the potential difference. So the charge is given, the potential difference is given, so all we need to do is put them in this equation and then we can solve for the capacitance. So here's what we do. C therefore becomes the charge, 2 times 10 to the power of 4. Okay, this is in coulombs, of course, and then we're going to divide that by the potential difference, which is 100 volts. Now remember that all of these will then be measured in farad. That's the unit of capacitance. So what we do next is this. Now look at this step, this simple step here. I'm going to write this in index form so that it makes it easy to solve without even using calculator. So we have 2 times 10 to the power of negative 4 divided by 10 squared. That's what gives us 100. And this is in farad. So what we now have is, when you apply the laws of indices, you now have 2 times 10. Now this is minus 4. Now, applying the law of indices, because this is a division here, it means we're going to subtract the power, so that is minus 2. And this is in farad. That gives us 2 times 10 minus 6 farad. Okay? Now, if you remember, we did talk about multipliers when you are dealing with capacitance of capacitors like this. And what we have here is times 10 to the power of 6. And what that makes it is microfarad. So this can be denoted microfarad. So we say C equals 2. This is the symbol for micro, representing the submultiple times 10 to the power of negative 6. So 2 microfarad. And that's the answer to this question. Here's another question. It says to calculate the charge on the plate of a capacitor of capacitance 5 microfarad and potential difference 50 volts. Now, in cases like this, what do we do? Now, you can feel free to pause the video and try this out yourself. Then compare your answer to what is gotten at the end of the video. And please do not forget to drop us a comment if you get the answer correctly. And if there's something you're not getting right, and please would like you to also put a question in the comment section as to what you would like us to explain better, so that you do get how to solve questions like this. All right. Now that you solved it, let's take a look at the solution. Do not forget that the capacitance of a capacitor is the ratio of the charge to potential difference. Now in this case, we want to find the charge. So this implies that the charge is a product of the capacitance and potential difference. So let's solve. The capacitance is 5 microfarad, and that means we have 5. Now remember, this is a submultiple, so it will be times 10 to the power of what? Negative 6. That's what we call the micro. And then, of course, it's in farad, so we then multiply this by the potential difference, which is 50 volts. Now when you multiply this, remember that charge is measured in coulombs. So what you need to do is say 5 times 50, and that will give you 250. Okay, multiplied by 10 to the power of negative 6, and this is in coulombs. Now you can rewrite this and say this equals 2.5 times 10. Now that means you have taken the decimal point 2 places forward, so you add 2 to this, and then you have minus 4 coulombs. And this is the solution to the problem. I do hope you got the same answer as you did. Good job. This question says, a capacitor whose plates have an area of 1.13 times 10 to the power of negative 3 meters squared and separated by a vacuum of distance 5 times 10 to the power of negative 5 meter is used to store charges. Now calculate the capacitance of the capacitor, given the permittivity of free space is 8.85 times 10 to the power of negative 12 farad per meter. Now when you have a question like this, this is how you solve it. Know that capacitance equals permittivity, but since this is a vacuum, so it will be permittivity of free space, multiplied by the area or divided by the distance separating the plate. So what do we have here? That is, we have 8.85 times 10 to the power of 12, negative 12. All of this now multiplied by the area. The area is given here, so we have 1.13 times 10 to the power of negative 3. And then all of this divided by the distance. So we have 5 times 10 to the power of negative 5. Okay? Now, all you need to do at this point is multiply this part at the numerator. So we have 8.85 rather, times 1.13. Now, that would give you 10.005 thereabout. So times, now what we have here is 10 to the power of negative 12, then minus 3. All of this divided by 5 times 10 to the power of negative 5. So when you divide this is approximately 2.0. Okay? So times 10 to the power of, this will give you negative 15. And negative 15, when you subtract this from it, minus times minus will give you plus. So we have negative 15 plus 5. So the final answer, C, therefore becomes 2.0 times 10 to the power of negative 10 farad. Okay, and that's the solution to this question. In electric circuits that involve the use of fixed capacitors, when one capacitor cannot give you the required amount of capacitance, sometimes capacitors are combined to either increase the capacitance or reduce the capacitance in arrangements known as series arrangement or parallel arrangement. Now, when you have a circuit with capacitors combined either in series or parallel, let's show you how to find the equivalent capacitance. That is, the capacitance rendered by the combination of those capacitors. So let's start with when we have series arrangement. Okay, now series arrangement means that the capacitors are connected, one led to the other. Okay, that is, you have one capacitor like this connected to another capacitor like this, connected to another capacitor like this. These are three capacitors connected in series. So let's call this C1, C2, and C3, connected in series on a circuit. Now, when you have three capacitors like this connected in series, and you're asked to find the equivalent capacitance or resultant capacitance. Now, the resultant capacitance is given by 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3. So in cases when you have more than 3 capacitors, you can also have the equation 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3 plus plus 1 over Cn until the last capacitor. So you continue to apply this equation like that. And then when you solve this, you get the equivalent capacitance by making C the subject of the equation. Let's practice how to find the equivalent capacitance of capacitors in series with the following examples. This question asks that we find the resultant capacitance of two capacitors, that is 2 microfarad and 3 microfarad connected in series. Now, when you are to find the resultant capacitance of capacitors in series, especially in cases like this where you have 2 capacitors, there's a simple and fast way to do that. I'll show you that, but first, I'll show you the root method we have learned, that is applying the formula directly and see how we solve it. So in this case, what we solve is this. Here's the solution. We apply 1 over C equals 1 over C1 plus 1 over C2, right? And that means 1 over C, which is the resultant capacitance, equals 1 over capacitance of capacitor 1 is 2 microfarad, then plus 1 over 3 microfarad. Now, I can easily work with this because both of them are in the same sub-multiples, microfarad. When they are different sub-multiples, I have to indicate what the sub-multiple imply in my calculation. Okay, so that's in that kind of situation anyways. Always make sure that they have the same sub-multiples before you put them in the formula. Otherwise, you will be getting a wrong answer. So in this case, the next step is to say 1 over C equals the LCM here. We have 2 microfarad. Okay, now this will go here 3. This will be 6 rather. Between 2 and 3 we have 6. So this will go 3 times. So 3 plus here we have 2. Okay, that will give us 5 over 6 microfarad. Now, whatever you do to the left hand side, ensure you do it to the right hand side as well. So that means C equals, just flip it, or you cross multiply depending on how you prefer to solve problems like this. So since this is 1 over C, I can just flip it to make C the subject direct, and then flip this other side and say 6 microfarad divided by 5. And that will give me 1.2 microfarads. And that's how you solve it using the formula direct. Now, don't forget that when you have 2 capacitors like this, there's a simpler way to do that, and it comes from what we have here. Take a look at this. 1 over C equals 1 over C1 plus 1 over C2. And now, this means 1 over C equals C1, C2, okay? And then here we have C1 plus C2, okay? Because when you do that, you have C2 here plus then C1 here. Now, what does that mean? It means C equals, now you flip this, which is C1, C2 divided by C1 plus C2. So easily I can just say my resultant capacitance is, now what is C1? That is 2 microfarad multiplied by 3 microfarad, all divided by 2 microfarads plus 3 microfarads. Now this will give you 6 microfarad squared, and then this will give you 5 microfarad. Now this cancels one of this, and then capacitance is 6 divided by 5, that's 1.2, and we are left with microfarad. And you see here that the answers are the same. So whether you use this method or this method, you always end up with the same answer. But this method is way faster as it just involves these numbers of steps. Anyways, that's the solution to find the resultant capacitance when you have 2 capacitors. In this question, we have a diagram, and then we have to find the resultant capacitance in the circuit being the diagram here. So across AB, we have 3 capacitors, C1, C2, and C3, and C1 being 3 microfarad, C2 being 5 microfarad, and C3 being 4 microfarad. Now we are to find the resultant capacitance. So here's the solution. Okay, so we have 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3. So which implies that 1 over C equals 1 over 3 plus 1 over 5 plus 1 over 4. Now we know the answer is going to be in microfarad since all 3 are in microfarad. So I don't need to indicate that in my calculation. However, if you want to, it's also allowed. It's not there's no specific law to that. It's all depending on how much detail you want to show in your calculation. Now, in this case, what do? We take LCM, okay? The LCM of 3, 5, and 4 is 60. So 3 goes in 60, 20 times 1, and then we have 20, plus 5 in 60. 5 in 60, that's going to be 12 times. So 12 times 1, that's 12, plus 4 in 60. That is going to be, 4 goes here, 1. I remember that, so that's 15. So we have 15, 12, and then 20. So 1 over C equals, when we add all of these, we're going to be having 20 plus this, that's 32. 32 plus 15, and that gives us 47. So 47 over 60. Now, what this implies is that C equals 60 divided by 47. and our answer is in microfarad. Now you can either leave your answer in fraction like this, or you apply your calculator to get your answer in decimal, and that will give you C equals 1.approximately 28 microfarad. Note this is an approximate figure. So this is the equivalent capacitance of 3 capacitors, 3 microfarad, 5 microfarad and 4 microfarad connected in series. Now that we understand the series connection and can find the equivalent capacitance or resultant capacitance of capacitors connected in series, let's learn what the parallel connection looks like and how we find the resultant or equivalent capacitance of capacitors connected in parallel. Now, in the case of parallel connection, all the leads of the capacitors are connected together. So that is when you have capacitor 1 connected both leads to capacitor 2 and then both leads connected to capacitor 3. What we have here is known as a parallel connection. Okay? All you need to look at is look at the leads. Are they all connected to the leads of the next capacitor? Are they all connected to the next one? And once all leads are connected like this, you know that you have a parallel connection. And in the case of parallel connection of capacitors like this, the equivalent capacitance resultant or equivalent capacitance resultant capacitance is given by C equals C1 plus C2 plus C3. So just like in the case of series connection, this time there is no fraction required. So whenever you have multiple capacitors in parallel like this, I will say C equals C1 plus C2 plus C3 plus plus Cn. N being the highest number of capacitors connected in that particular arrangement, which is parallel connection. And this is how we find the capacitance of capacitors connected in parallel. Let us apply this to a number of examples. 3 capacitors, 2 microfarad, 3 microfarad, and 5 microfarad are connected in parallel. Find the resultant capacitance. Okay, so in this case, what do we do? The solution. C equals C1 plus C2 plus C3, since we have 3 capacitors here. So it means the effective capacitance or resultant capacitance therefore becomes 2 microfarad plus 3 microfarad plus 5 microfarads. So that means the effective capacitance or resultant capacitance therefore becomes now 2 plus 3. Now remember, they all have the same submultiples, so we can just collect that as a like term and then add the figures together. So 2 plus 3 gives 5, 5 plus 5, and then we have 10 microfarads as the solution to the problem. In this question, we see that if the effective capacitance of the system above is 9 microfarad, we have to find the value of C. And here we see 2 capacitors connected in parallel, one being C, the other being 4 microfarad. Now the combination of these two is what gives the 9 microfarad. And since they are connected in parallel, it means the effective capacitance is the sum of their individual capacitance. Hence, in our solution, we should have C plus 4 microfarad to give us 9 microfarad. Now what this implies is that C is 9 microfarad minus 4 microfarad, and this will give us 5 microfarad. So the solution to this question is 5 microfarad. Quite a number of questions that you'll be asked to solve for equivalent or resultant capacitance will involve a combination of both series and parallel connections in the same circuit. Like what you see on the board here now, we have a 5 microfarad capacitor connected in series with a parallel combination of 3 microfarad and 2 microfarad. Now, when solving questions like this, you have to be able to visualize the connection and see what the primary connection is. Okay, like in this case, we see that the beginning of the circuit is here and this is the end of the circuit. And we see that it's a single line of connection. So the primary connection here is series connection. So before you can continue to find the final effective capacitance here, you have to first break this down so that it becomes one capacitor. So that is, you are going to find the resultant capacitance at this point first. Then when you get a single capacitor that represents these two combined, you now solve it in series with this 5 microfarad. Okay, so here will be the solution to find the resultant capacitance. Resultant capacitance. In the circuit above, we're going to start with the parallel connection. So parallel capacitance will now be what? 3 microfarad plus 2 microfarad. And this will give us 5 microfarad. So that is these two combined to give us 5 microfarad, leading to the fact that the new circuit we now will involve two capacitors now that are both 5 microfarads. Okay, since this 2 gives us 5 microfarad. This is our new circuit. And then remember, when you have in series like this, what do? Remember, we have 2 capacitors here. So we can just say the effective capacitance becomes C1 times C2 divided by C1 plus C2. So what we have is 5 times 5 divided by 5 plus 5. And this would give us what? 5 times 5, 25. 5 plus 5, 10. So what we have is 2.5 microfarad. And that's the solution to a problem like this. This question says, in the circuit above, if C1 is 5 microfarad, that is, this capacitor has a capacitance of 5 microfarad, C2 and C3 are equals 10 microfarad each. That is, C2 is 10 microfarad, C3 is 10 microfarad as well. And then C4 is 6 microfarad. Now we have to find the resultant capacitance. The resultant capacitance. Now, how do we solve a problem like this? Recall that I mentioned that when you have a combination like this, you have to be able to visualize what the primary connection is. So in this case, we see that we have a parallel connection, but within the parallel connection, there's this series arrangement here. So it means you have to first tackle the series arrangement and find the effective capacitance at that point before you then go on to find the effective capacitance in the entire circuit. So we're going to start with the series. The part that is in series means that we're going to have this times this. So C2 times C3 divided by C2 plus C3. And what does that give us? Now C2 and C3 are the same. So 10 microfarad times 10 microfarad. So 10 times 10 divided by 10 plus 10. So that will mean that C series is what? 100 divided by 10. And that divided by 20, I mean. And when you divide this, what do we have? That would give us 5 microfarad. So that is this series arrangement combined to give us 5 microfarad. So the effective capacitance then become C1 plus C series plus C4. So what do we have there? C1 is 5 microfarad plus C series, another 5 microfarad, plus C4, which is 6 microfarad, giving the total capacitance to be 16 microfarad. And that's the solution to this problem. This question says, how can 3 capacitors, 3 microfarad, 4 microfarad, and 4 microfarad be combined to give an effective capacitance of 5 microfarad? Now, feel free, challenge yourself to try to solve this problem. Okay? Then compare how you got your answer with the process we did here. You see, these kind of questions are those that you can just test yourself with. Sometimes you don't have to always go on and begin to solve and calculate on paper before you get your answer. Some of these things you can even do the calculations in your head and then you can arrive at the answer. I mean, take a look at this. If we connect the 3 of them in parallel, we know that what we'll be having is 3 plus 4 plus 4, and that would give us what? 11 microfarad. Okay? And that 11 microfarad is way more than 5 microfarad, so we cannot therefore connect in parallel. Now, how about when we connect in series? If we connect in series, the effective capacitance will be 1 over 3 plus 1 over 4 plus 1 over 4. And then when you do that, that should give you 1.2 microfarad, which is way lesser than the 5 microfarad that we require. So the only thing you can do is to combine 2 in parallel, and then to combine 2 in series and then in parallel with the other one. And when you do that, you should be able to reduce the capacitance. So what do we do here? Let's test. So if we combine 4 and 4 in series, what would that give us? If we do C2 and C3 in series, okay, that will mean that 1 over C series is then 1 over 4 plus 1 over 4. Of course, that is C series becomes 4 times 4 over 4 plus 4, which will give us 16 divided by 8, and that will give us 2 microfarad. So that is, these two combined in series will give us 2 microfarad. So now that we have 2 microfarad from this and we want to get to 5, the only way we can get to 5 is to add it to this, which means we need a parallel connection. So we now say C1 and C4 and 4 connected in parallel will give, so that will mean we have 3 microfarad plus 2 microfarad to give us 5 microfarad. So your effective connection should look something like this. That is, you're going to be having so where this is 3 microfarad, this is 4 microfarad, and this is 4 microfarad. This is the connection that gives us 5 microfarad effective capacitance when we have these 3 capacitors to work with. So don't forget, these kind of questions test how well you can solve for capacitors in series and parallel and then combine them in one circuit. And if you do have any question on this, please feel free to drop them in the comment section. And if you are yet to be subscribed to the channel, kindly take a moment of your time to click the subscribe button. And don't forget to help us reach many more students like you to get access to the beautiful work that we are doing right here on our channel by sharing the video. Please ensure that you share the video and encourage your friend to also like the video and drop us a comment. Thank you so much. We'll continue in our study as we now go to look at energy stored in capacitors. As you energize a capacitor in a circuit, what happens is that the potential difference across the plate V moves from 0 to a final value of V, which implies that it's going to have an average potential difference. So the average potential difference is then 1 over 2 0 plus V, which will give you 1 over 2 of V. And at the same time, the charge on the capacitor, charge Q on the capacitor, will go from 0 to final value of Q. Now remember that each of the plates has the same charge. So that means the average charge is still Q in this case. Now when you multiply these two, you get what is known as the energy stored in the capacitor. So the energy stored in capacitor is therefore half V multiplied by Q. Okay, so this is how we find the average energy stored in capacitor using this equation, half QV. Okay, but we also know that C is Q over V, right? So if that's the case, it means that we can write that Q equals CV. So if Q equals CV, this equation, energy, will now be what? 1 over 2 multiplied by Q, which is what? CV, multiplied by V to give us half CV squared. Okay? Now, another way to put this also is in terms of V. Okay? And if we put this in terms of V, if V, since V equals Q over C, it implies now that energy also will be 1 over 2, okay, Q multiplied by V, which is what? Q over C. So that will give us 1 over 2 Q squared over C. So you see this equation here, and this equation. The three of them applies whenever you are asked to find the energy stored in a capacitor. Let's apply them in a couple of examples so that you see how we use them to solve for energy stored in capacitors. This question says, a 5 microfarad capacitor is subjected to 1000 volts across its terminals, and we are to calculate the energy stored in the capacitor. So here's how we solve this. Okay, we know that we are given C equals 5 UF, okay, and we are given V equals 1000 volts. Okay, so energy stored would then be half CV squared. So this will be the equation that works in this case. Okay, and when we apply this, it means we have 1 over 2 times 5 times 10 to the power of 6 multiplied by, remember this is minus 6 rather, because it's microfarad, multiplied by 1000 squared. Okay, now when we apply this here, what do we have? It means E becomes, this will give you 2.5 times 10 to the power of negative 6 times, now this will give you what? This will give you 1 million, which is 10 to the power of 6 as well. So when you apply this cancels this easily. So that means the energy stored is 2.5 joules. And that's the solution to this problem. For a more complex example on how to calculate the energy stored in capacitors, let's look at this question. When we are asked to calculate the energy stored in a 2 microfarad capacitor, that is this particular capacitor here. Okay, now when it comes to questions like this, it's going to build on what you've learned before now. Now, remember when we were dealing with basic electricity and we have like 2 resistors in a circuit like this, where the 2 resistors are in series. We said that they act as voltage dividers such that this 100 volts will divide itself into 2, where we have V1 here and V2. So V1 is across the terminals of this particular capacitor here, and V2 is across the terminal of this capacitor. This will split itself, yeah, and we know that V1 plus V2 equals 100 volts. That we can establish from that knowledge there. Another thing is, because there's just one direction of current here is in series, it means that the charge stored in individual capacitor is the same. Hence, there's nothing like Q1, Q2, we just have Q, which is the charge stored in the capacitors. And in order to find the value of this Q, we need the effective capacitance. So to solve this question, you're going to do it in the following steps. So follow me as we go through how we solve this problem. So the first thing is to find the value of Q. Okay, to do that, we need the effective capacitance of this circuit, that is the final capacitance. So C equals C1 times C2 divided by C1 plus C2, since it's in series. So that means we're going to be having 2 times 3 over 2 plus 3 to give us 6 over 5. So effective capacitance is 1.2. Remember, it's in microfarad, so UF. So that means we have 1.2 times 10 to the power of negative 6 farad as the effective capacitance of this circuit. Now that we have the effective capacitance, applying that C equals Q over V, which implies that Q will be what? CV. We can use this to find the value of the charge stored in the capacitors. So charge across the capacitors would therefore be Q equals C. Okay, just work with one of the capacitor, with the effective capacitance rather. So we have 1.2 rather. Yeah, 1.2 times 10 to the power of negative 6. Okay, multiplied by the potential difference across all the capacitors. So since we have 100 volts here, I will put that here. So that means Q therefore becomes, now when you multiply this, you're going to get 1.2 times 10 to the power of negative 4 coulombs as the charge stored in the capacitors. So each of the capacitors have 1.2 times 10 to the power of negative 4 coulombs in each plate of their capacitors. Okay, so now that we have the value of the charge, we can then go on to find V1 or V2, working with just one of the capacitor. So V1 is going to be what? Remember, from this equation, we can make V the subject now. So it will be V equals what? Q over C. So they have the same Q, so over C1. V1 equals Q over C1. So applying that, V1 will be what? What is Q? 1.2 times 10 to the power of negative 4 over C1, which is 2 times 10 to the power of negative 6. What does this give us? Now, when you apply this, what are we going to have? I will have 0.6 times 10. Okay? Now, this is minus 4 plus 6. That will give us 2. Minus 4 plus 6. That will give us 2. Okay? So now that we have this, it means V1 equals 0.6 times 100. And that will give us 60 volts. Okay, so if this is 60 volts, it means that this one will be 40 volts. That's just what it means. But you can test just to be sure. Remember I mentioned that V1 plus V2 will give you 100. Just to test that, let's apply the same thing here. That is, V2 is supposed to be 1.2 times 10 to the power of negative 4 divided by 3 times 10 to the power of negative 6. And then you see that V2 here becomes, now 1.2 divided by 3 will give you 0.4. So times 10 to the power of 2. And you see that V2 will give you what? 40 volts. So you see 40 plus 60 gives you what? The 100 volts. So it tells you that the equation works. So now that we have the value of V1, we can then go on to find the energy stored in the 2 microfarad capacitor. So energy equals half CV squared. So that's what we're going to apply. So what we have now is 1 over 2 times, this is what? 2 times 10 to the power of negative 6 times V. V1 is what? 60. So when we apply this, what do we have? 2 here 1, 2 here 1. 1 times 60. And then we have 60 times 10 to the power of negative 6 joules. Okay? Or you can just say E equals 6 times 10 to the power of negative 5 joules. And this is the solution to this question. Now, I'm going to encourage you, I would like to encourage you that you practice more. You see, the thing about questions like this is that the more you practice, the better you get at solving questions like this. So please check out for questions from the WAEC exams, from JAMB exams, and any other exams that you usually write. And pick out questions on capacitors and capacitance. Try them out using the tips that we have given across the video so far. And don't forget to also practice on electric field because they fall under the same topic. What we have been doing so far is electric field, and we end it on capacitors and capacitance since it has 2 parts. Please practice with all of the questions you can find on the topic. And if peradventure you come across a particular question that is slightly tough and you need some help with, please drop it in the comment section. And we promise to make a video explaining how to solve those questions to you. And please don't forget, if you're not subscribed to the channel, this will be the time for you to quickly click the subscribe button. Join the family and help us to grow and ensure that we impact more lives as we continue to give you more content like this to help your academic journey and make it as smooth as possible. And don't forget to help others by also sharing the video so that they too can have access to the amazing work that we do right here on Oya Learn Your Flawless School 2. So please ensure that you share the video, like the videos, drop comments, and keep your engagements coming. Thank you so much for being part of the video. This brings us to the end of week 3, which is electric field and then capacitors and capacitance. I'll be seeing you in the next video. Bye for now.